Good afternoon. Jim Nichols is a senior statistician retired from the Fish and Wildlife Service and Geological Survey. He earned his master's at Louisiana State University and his PhD from Michigan State University. He's contributed to most areas of quantitative ecology, especially those related to population dynamics. One important thread throughout his work is observer detection. Observers don't catch everything. This is the equivalent of non-response in our surveys. On one hand, if you think non-response is hard for cell phone surveys or exit polls in rural counties, what about for ducks? On the other hand, non-response may be what you want when studying tigers, and camera traps are ideal for subjects you'd rather not meet up close. But detection is a nuanced parameter. You want to estimate it correctly, but then integrate it out. What are important are the demographic parameters. In the camera trap tiger study, actions taken from the estimates and study results greatly benefited the Indian communities near the study and also for tiger management. In a similar way, his team affected policy on their study on habitat fragmentation and species survival. He also has thought a lot about the cost of monitoring. In economic, social science, or biostatistical areas, the current population survey, current price index, or national health and interview examination survey could be thought of as large-scale monitoring projects. For waterfowl, monitoring consists of flying aerial transects across North America at 100 miles an hour, 100 feet off the ground. On top of the cost of planes or helicopters, pilots and observers, there is also the risk to life. Jim pushed to have this costly data tied to important decisions. That was the start of adaptive harvest management, where data and analysis were derived from the decision process. This is what Jim will talk about today. These decision-making methods have evolved to resolve many thorny and complex natural resource problems, and an active community of practitioners has grown to learn and work together in interior. Adaptive management is now an interior policy. All this to make better decisions. So, Jim, welcome. We look forward to your talk.
Well, thanks very much, Mark. Thanks, Jan, as well. I'll try to see if I can figure out how to share a screen here. So I really appreciate the opportunity to make a presentation here. I just make one slight modification to your introduction, Mark. You're real generous. Thanks very much. But I don't view myself as a statistician. I'm kind of a biologist who knows a little statistics. And anyway, that's the way I see myself, but we'll proceed and see how we go. So Mark was real interested in my talking about decision making. He was sort of insistent on that. And I'm very much in agreement with him that decision processes are really important and can assume more importance, I think, in society here these days. And it's something that I don't think receives the attention it should. And so that's kind of an overall motivation for doing this, I guess. So I'll start by making the simple-minded comment that I believe that statisticians and scientists are usually involved with a couple major kinds of endeavor. Okay, one of those is science. We like to kind of understand how the world works, learn stuff. And the other is making smart decisions that move systems towards objectives that we have set to go to places we'd like them to go. And so thankfully, I believe that statisticians have been integrated really well into most science. That is, I can't think of a scientific discipline that I know anything about anyway, that hasn't recognized the importance of statisticians in drawing inferences and discriminating among competing hypotheses about how the world works. And I think that's great. That's as it should be. But with the decision processes, it's not so much. Statisticians haven't been integrated to the degree that I believe they could, and to a degree that would be, I think, beneficial to basically society in general. Okay, let's see if I can, so my, I'm trying to figure out how to, oh, there we go, how to advance myself, sorry. So one thing that's interesting to me is that statisticians and other scientists as well often lack training in decision processes. And this even is true for applied sciences such as engineering, conservation biology, public health, places where decisions are front and center. That's part of what we do. And yet you can get PhDs in some of these programs without ever having a course in how to make a smart decision. And indeed, it's even more surprising because life itself can kind of be viewed as a sequential decision process. I've got a few quotes here. One, Gandalf talking to Frodo in Lord of the Rings. Another verse from a Richie Havens song. Richie Havens was one of the original Woodstock guys, singer-songwriter. And then a couple of months ago, I was reading a Dr. Seuss book for about the 30th time to my 3-year-old granddaughter, and came across this quote about mind maker upper, excuse me. So anyway, the point is a lot of people realize and recognize the importance of decisions, and it's something that is just, decisions are pervasive basically in our lives. All right, so I believe anyway, decisions are important, but why statisticians? Many, if not most important decisions are characterized by various flavors of uncertainty, usually a bunch of kinds of uncertainty. And the best way I know to think about uncertainty anyway is to use probabilistic thinking. And unfortunately, a lot of folks aren't comfortable or familiar with what I think of as probabilistic thinking. And of course, statisticians are. Now, the motivation for this presentation then is kind of simple. It's basically, I think making good decisions is increasingly important in a whole bunch of areas now in our lives, but relatively few of us are trained in decision processes. And as far as this particular audience here, I believe that statisticians are pre-adapted, if you want to think of it that way, to taking leadership roles in a lot of the technical aspects of decision making. So that's sort of the reason for trying this. And as far as the content here, that'll be fairly simple and straightforward. What I'll try to do is describe one kind of decision process called adaptive management. Again, there are a bunch of decision processes we could talk about, but this is one that ends up being fairly useful in most of the problems that I've ended up encountering. And it's basically a flavor of decision-making that deals with recurrent problems that are characterized by lots of uncertainty. And that's the world I live in for sure. And so I'll illustrate the process using an example. It's an example that Mark and I both, for fair, or at least non-negligible parts of our career, ended up working on. It happens to do with duck harvest. And I'll sort of have hopefully some general descriptions of what adaptive management is, and then try to follow along with this real world example to make the sort of general comments a little bit more tangible, at least for this one specific case. And while doing so, I'll try to note the roles of statisticians in this process. Okay, so I'll start out just with this example itself, just a real brief couple of introductory slides on this. Waterfowl harvest management. Each year, the federal government is charged with developing hunting regulations for waterfowl in 4 major administrative flyways in North America. And the basic idea is they'd like to provide sustainable harvest opportunities for waterfowl hunters, where by sustainable, we mean that waterfowl populations don't wink out on us. They go ahead and persist just fine as healthy populations into the indefinite future. All right, so what's at stake? Lots of birds, lots of hunters, not a huge amount of money, but not a trivial amount of money anyway, associated with economic input with this particular process. Now, there's a legal mandate that the U.S. Fish and Wildlife Service, who administers the regulations that they're basically under they have to abide by. And the legality is based on this Migratory Bird Treaty Act of 1918, which was between the US, Canada, and later on Mexico. And it provides two potentially competing objectives, but luckily it specifies which one of those is to be considered primary. So the basic statement is that sport hunting of waterfowl should be permitted to the extent that it's compatible with production and maintenance of waterfowl populations. So basically the primacy is healthy populations. And as long as we have them, we would like to be able to permit sport hunting as well. So it's a real reasonable sounding objective statement, but if you think about it a bit, or certainly if you've been immersed in some of the wars as Mark and I have, you recognize it's kind of a setup for dissonance and controversy. All right, so duck harvest management has a long history then, and as early as the 1930s, the U.S. Fish and Wildlife Service and Canadian partners started developing survey programs to estimate things about how waterfowl populations are doing. So these things have been ongoing for quite a long time. So I came and started working with the Fish and Wildlife Service in 1976, and I was viewed as a sort of a technical guy, a quantitative biologist. And so I was charged with thinking hard about how you estimate stuff about waterfowl populations, abundance, survival, recruitment, harvest, things of this nature. I was also charged with thinking about models for how you translate the effects of different regulations and hunting regulations into population responses. In other words, how do our hunting regulations affect populations? And those were my two sort of primary things that I worked on for the first few years with Fish and Wildlife Service. Now, my very first so-called set of regulations meetings, these formal meetings, occurred in 1977. And I went to meetings at a couple of these different flyways, and then the big meeting was held at the Department of Interior, the Interior building in downtown DC. And there was a real asymmetry there that struck me and seemed not quite right to me, and I'll articulate that here. The asymmetry was that those of us technical folks spent an awful lot of time and effort trying to kind of get the estimation and get the modeling right. In other words, there was as much statistical rigor as we could build into that. And indeed, this was even in the 70s when I was there, the importance of statisticians was recognized, and we had bona fide math stat people working on these problems with us. So statistics was front and center. But then the interesting thing was when the final decision then about, okay, what regulations do we impose, when that decision came along, it wasn't associated with that rigor and sort of, well, I'll just say the basic way it happened is the estimates and the model-based predictions were given to sort of higher level policy folks. And the policy folks would look at them and, sort of render Solomon-like decisions and say, well, I think we'll pick these regulations this year, given all this stuff. And so some grand integration of the mind was apparently going on, but it wasn't transparent. It wasn't necessarily easy to defend. And the result was lots of arguments and dissatisfaction among hunters. So anyway, this asymmetry between the effort and rigor that went into the estimates and models as opposed to the actual decision process or the end step of the decision process itself was really striking and something that made no sense to me. And so I grabbed pom-poms and tried to be a cheerleader for the next 20 years and suggesting we do things a little bit differently, and was absolutely ignored. I realize now that cheerleading wasn't a smart way to have gone about this. But a fellow named Fred Johnson came along. I ended up then assuming some other duties, doing some other things, but a fellow named Fred Johnson came along, had the same exact reaction as I did when he went to his first set of regulations meeting. So came back and said, okay, we just can't allow this to keep happening. So I'm going to go ahead, even if the supervisors don't necessarily aren't asking me to do it, I'm going to develop an ad hoc working group of folks and think about an approach to decision making, this adaptive management approach, And I'm going to think about using it for an example population, mid-continent mallards, one of the largest and most important waterfowl populations that's hunted in North America. And Fred got this group together and they actually developed a process which was then implemented in 1995. And that's what I'll kind of be talking about. So the whole presentation will deal with adaptive management. Just if you had to sort of summarize and give it a quick one-sentence definition, I'd call it a process for managing in the face of uncertainty while simultaneously trying to reduce that uncertainty. Okay. All right, so adaptive management, I think I mentioned earlier on, it's basically developed for recurrent decision problems that are characterized by lots of uncertainty. So what's a recurrent decision problem look like? Well, here we have a timeline that has 3 different decision points or times. And the idea is that at any point along this line, at any decision point, we decide on an action, okay? We impose that action on the system, and then there are 2 arrows coming out. Basically, that action causes 2 things to happen. It causes a return, that is, hopefully something happens that's relevant to our objectives that we've set out. And then the other thing the action does is drive the system to a new state. Now, the kind of uncertainty that adaptive management is developed to specifically deal with is the models that predict those 2 arrows coming out. In other words, the models that say, okay, if I implement or impose this particular action, impose it on the system, then I expect this sort of return, and I expect this sort of, I expect the system to look like this the next time step. And in many cases, there's a lot of uncertainty about that. So much uncertainty that we actually have multiple models, plausible stories about how actions are translated into returns and changes in system state. And it's reducing this uncertainty that the process of adaptive management was at least originally developed for. Okay, so in terms of this decision problem, we impose an action, we get returns, system goes to a new state. Once again, now with the system in a new state, we take another action and same thing happens. We get some return from that and the system moves along as time goes on. All right, now adaptive management, how do we implement or think about then a process for dealing with this kind of decision problem? Well, adaptive management is just a subset of what a lot of folks would call an informed decision process. It's just a special case of it. And in basically all informed decision processes, you need these 6 components, kind of elements or things you need in order to be smart about making decisions. First one's objectives, second one's management alternatives. The third one is models or some way of predicting how the system responds to your actions. In the case of multiple models, we have to have measures of model credibility for a couple of reasons I'll explain. And then we like a monitoring program to estimate the state of the system and perhaps other variables that are relevant to our objectives. And then finally, a decision algorithm, something that takes all this stuff, these first 5 elements, and says, okay, conditional on all these, here's the smartest thing to do at this point in time. The 2 bullet points at the bottom make an important point that I think is fairly important. Number 1, the first point there says that elements 1 and 2 are basically based on societal values, law, politics, stakeholders. Those things incorporate the views of a whole lot more people than just statisticians and scientists. Statisticians and scientists certainly can have their perspectives and enter their views, but these objectives and management actions are based on stuff way, way beyond just that group of folks. On the other hand, elements 3 through 6 are very much the purview of scientists and statisticians. Again, other folks can participate, but scientists and statistician types usually have a leadership role there, as is quite appropriate. All right, so we'll zip through these elements. I'll say something general about them and then talk about the duck egg example as well. So our key element 1 we'll call objectives there. I've written down a few things about objectives. The third bullet point there is kind of a big deal, and that is that objectives drive the management process. That is, everything else, all of the other elements of the informed decision process are basically viewed as conditional on and derive from what the objectives are. In other words, I don't know how to build models, or I don't know how to design a monitoring program until you tell me what the objectives of the process are. So it's a big deal to get those things right. And of course, they reflect much more than just science. They reflect societal values, things we value as humans. There's legal stuff and policy as well. And I'll just say this very briefly as sort of a side comment. I know during the first year, especially of COVID, it used to irritate me a little bit that when you turn on the television, and very frequently you'd hear the phrase, well, what we've got to do is follow the science. And maybe it was meant in the right way, but I'm guessing a lot of folks got the wrong impression there. And that is that that somehow science dictates what you should do for any particular problem. And of course, with the respect to any problem, that's not true. In other words, it's got to be conditional on objectives. And in the COVID case, I can think of objectives, for example, that wouldn't have led to these cavalier statements about, well, we'll do this or this as a way of following the science. Anyway, so science doesn't give you objectives, but conditional on objectives, then the notion of applying science makes plenty of sense. All right, so the duck example here, the duck harvest objective, we could say it's in a real brief manner by just saying what we were trying to do is maximize long-term harvest. Now, initially, that sounds counter to the sort of statement I made about the Migratory Bird Treaty Act, which said, wait a minute, we got to have healthy populations, and conditional on those, we want to be able to have harvest. But if you think about it, if harvest is viewed over a long time horizon into the indefinite future, the only way we're going to have harvest in the future is to have healthy waterfowl populations. In other words, you can't say wipe out all your birds in year T and maximize harvest there, because then you don't have any harvest to accumulate in subsequent years. That's pretty obvious, I guess. In addition to that general sort of objective, there was also a constraint built in early on, and that was that folks wanted to maintain a fairly large mid-continent mallard population size. It was a goal of something called the North America Waterfowl Management Plan, which was actually set about a decade before the implementation of adaptive harvest management. But basically, for historical and a few other reasons, folks decided that 8.8 million mallards was a good number to have. And it basically, what that meant was the hunting public was kind of not so happy when in years that had gone under that, and everybody was pretty happy sort of after that time. And so what we did was say then that the objective function was not just maximizing this sum of harvest, this HT, over some long time horizon, but it was the sum of that harvest multiplied by a utility function, where the utility was a function of the predicted population size the next time step. And so to make that hopefully more obvious, it basically said utility will go ahead and give harvest a value of 1 whenever our expected population size the next time step is 8.8 million or bigger than that. But when it's smaller than that, then we're going to devalue harvest. So it was another sort of hedge, conservative hedge, if you will, to prevent smallish numbers in the population. Okay. All right, so our second key element was management options. Don't have a lot to say about this in general. It's determined by managers based on feasibility and political issues sometimes. Now, in the duck case, basically we had these 3 discrete sets of hunting regulations. And so the decision each year was which one of these 3 sets, or actually a 4th, which would be a closed season, which one of these things do we actually select and impose on the hunting public. There are 4 columns there. They represent the 4 administrative flyways: Atlantic, Mississippi, Central, and Pacific. And there are 2 key elements of the hunting regulations then that are subdivided according to this: R, restrictive regulations; M, moderate regulations; and L, liberal regulations. So one of those was so-called season length, the number of days in the hunting season. And the other, I've labeled basic bag here, was the maximum number of birds that a hunter can bring home in or have in his possession, his or her possession in any one day of the hunting season. And so these were the two key elements of regulations, and they varied according to these again, three different basic packages: restrictive, moderate, and liberal. Now, these things, as you can see, could be specified very precisely. There wasn't much uncertainty at all in specification of season length or bag limit. But there was uncertainty in the way those things translate into responses of the population itself. So, for example, here are sort of fitted frequency distributions, distributions for the predicted harvest rate for one age sex group of mallards, adult male mallards, for the three different regulations categories. So despite the precision of being able to say how long the season is and how many birds one can take each day, as you can see, there's substantial variation in this thing called harvest rate, which is basically the fraction of individual birds that start out at the beginning of the hunting season that end up dying as a result of hunting during that season. It's something very close to that. So this is a particular flavor of uncertainty that we need to be able to deal with, and indeed this process does deal with. All right, the third key element then are predictive models. First comment there is modeling isn't optional. If you don't have any basis at all for making a prediction about what your actions are going to do, both with respect to your objectives and to the state of the system, then you might just as well hand a monkey a fair coin or a die and make your decisions that way. A few other comments about the models. In the waterfowl example, we basically had 4 specific models, and those 4 specific models all followed this one generic framework, which is just a sort of a generic population models for a duck population. And what it's done is divide the year into 3 different pieces, and you have a survival probability associated with each one of those pieces. Now, a key is the piece during the hunting season there, where you've got this K, this kill rate or fraction of birds that dies as a result of hunting. You've got a survival rate for the winter and a survival rate for the summer as well. You've got this A thing thrown in there, which is basically a reproductive rate. It's influenced by numbers of ponds on some key breeding areas. As ponds go up, reproductive rate goes up. As BPOP, or the breeding population size, goes up, the reproductive rate, not the number of young, but the young per adult actually goes down in a negative density dependent way. But this is just a basic sort of a bookkeeping population model. And then the sort of the variation, or where the 4 specific models came from, was 2 sort of endpoint or extreme models of the effects of hunting on survival. One of those we'll call additive, which is basically an additive competing risk model. The other we'll call compensatory, which essentially said that there's at least for a set of harvest rates, variation in those harvests bring about little variation at all in overall survival rates. And there are a couple of mechanisms, if anybody's interested, we could talk about afterwards, that may produce that. So 2 different flavors of models, ways of modeling hunting and its effect on survival. And then 2 different ways of modeling recruitment rate, one which was a weakly density dependent sort of function or model, and another was strongly density dependent. So you got 2 ways of modeling mortality, 2 ways of modeling recruitment rate, and the combinations of those lead to the 4 different models that were used in the adaptive harvest management process. All right, another thing we need then in the case of multiple models, which we had in this situation, was measures of model credibility. And we'll call these things model weights, call them something different, I guess, but these weights basically reflect the relative credibility of a model, where that credibility comes from the model's predictive ability relative to the other models in the model set. And these weights sum to 1 for all the members of the model set. Models with higher weights end up having bigger influence over your decisions, and some kinds of decision processes, such as the adaptive management process we're using, actually permit learning. And this learning is reflected in the evolution of these model weights, the evolution of our confidence in these different models and their abilities to predict. Okay, the expression for doing that, the so-called model weight updating, the evolution of model weight should look kind of familiar to most statisticians. It certainly has a Bayesian flavor to it. If we look at the numerator here, we've got the probability at time t for model I. This is the thing that we'll call a model weight. And so the probability at time t, that model weight basically incorporates or encapsulates all of the predictions that have occurred up until time t and how relatively well that model has performed with respect to those predictions, to making predictions, how well they have done in terms of actually predicting what happened. And then we got some new stuff at time t+1. This probability of data at t+1 given model I basically says how consistent are the new data with the processes incorporated or encoded into model I. In other words, how likely are these data to have arisen if model I represents a really, really good approximation of reality. So that thing's the denominator, and then the numerator, and then the denominator is just the sum of that product for all the models in the model set. And it gives us something then that looks very much like a posterior. It's the weight at time t+1 for model I, given now this new data, and of course, given the prior model weight as well. And we're going to call this thing the information state, basically the vector of these model weights at any point in time. It reflects or encodes our information about the relative utility of those different models for predicting. All right, element 5 then is monitoring. There are a whole bunch of reasons we monitor. 3 of the most important are listed here. We want to determine system state for making state-dependent decisions. We want to determine system state for and other variables that are relevant to objectives to assess the degree to which our objectives are being achieved. And then we also want to determine system state for this purpose of learning, that is for using it in expressions like the previous ones to update our model weights and get ideas about which models perform best. So this, with respect to the state-dependent decisions, this is an example of a state-dependent decision matrix where we have our mallards on one axis in this key environmental variable that influences reproduction, the ponds on another axis. These are expressed in millions, and they have to do with this particular breeding grounds where this mid-continent mallard population tends to hang out in the wetlands associated with them. So the 4 different colors represent 4 different regulations, basically sets of regulations, which end up being recommended depending on where the system is in this 2-dimensional state space. So the blue is a good place to be, right? The bottom right hand corner of this matrix is basically a place where you got lots of mallards and lots of ponds. So that's a good place. And the blue ends up being liberal hunting regulations. Any one of those blue squares, if your system falls in there, you impose liberal hunting regulations. The dark green is moderate. The kind of turquoisey or lighter green thing is restrictive regulations. And then the purple would be something like a closed season. The upper left-hand corner of this the matrix is a place where you don't want to be, not many ponds and not many mallards. But the notion of state dependence here is very important. You tell me where I fit, where our state is based on our monitoring in this state space, and I tell you what regulations we're going to impose. Okay, well, how do we get that thing? That's kind of important. And the idea is that that comes from, a matrix like that comes from some sort of decision algorithm. In our case, it has to be a dynamic decision algorithm since we're dealing with these dynamic and recurrent decision problems. And sort of the workhorse up to now has primarily been stochastic dynamic programming as a way of doing Richard Bellman stuff that he developed back in the 1950s as a way of deciding what's the smartest thing to do. And there are a couple of other extensions of this which are proving really useful to us and will certainly be more so in the future. Okay, so those are the 6 elements of any informed decision process. We've talked about them with respect to how they fit into this specific kind of decision process called adaptive management. And then we've tried to follow through with this duck example as sort of one example of how this process can be implemented. So we put all these things together then into this kind of outline here in this slide of the iterative process itself. So the very first bullet point, we can view this as our first time step. And what we'll do is derive and implement an optimal management action based on all the other elements, that is, except for basically all the elements of the decision process. In other words, it says, you give me an objective function, you give me the set of actions to choose from, model set, model weights, current state of the system, and I can use my decision algorithm then to figure out what's the smartest action to take at that time. That action then brings us into this iterative part of the second bullet there, the iterative part of the process. The action drives the system to a new state. We observe that new state of the system through our monitoring program. We then update model weights based on the new state of the system. And then we derive an optimal management action again. Okay, so a lot of this stuff from up above, from the first time step, is unchanged. The objective functions, the actions are available to us in the model set. But what's changed are the current state of the system and the model weights. And this causes us the need to go through this decision algorithm again and decide what's smartest to do at this second point in time. So we derive the optimal management action, implement it, and go back and observe the state of the system and so on, and repeat this over time. And the stars there, the asterisks, make the point that statistical input from statisticians is a big deal to this process. They're important for developing the model sets, the model weights, estimating the stuff in the current state of the system, and then also it's this deriving the optimal management action, which comes from the decision algorithm itself. All right, I want to say a couple of things about learning in kind of the scientific component of adaptive management. Adaptive management, one of the things that makes it attractive to me is this ability to reduce uncertainty as part of the management or decision process. And indeed, what adaptive management does is insert a scientific step into this larger decision process. So we talked about how model weights are updated over time as a function of current model weights and new stuff, new information. And basically that probability in that equation of the updating equation, that probability of data at t+1 given a particular model, that's essentially looking at the difference between the observed state of the system and the predicted state, basically saying how well did this particular model do at predicting what we actually see. And of course, that ends up being the key step of science. In other words, we didn't give a flip about management. We're just trying to learn stuff and viewed these as four competing hypotheses that we wanted to discriminate among. That's exactly what we would do. We'd follow this scientific step that's embedded within this decision process. Anyway, and then learning is reflected by the evolution of the model weights. So I'm going to put this slide here. I apologize for it in a way because I want you to just focus on, I know that's not fair, just focus on the bottom part here, just mainly for time reasons. But the bottom portion of this ends up showing the evolution of model weights for these four competing models in the duck harvest management process. Now, in 1995, we started out with equal weights for each one of the models in the model set. Now, we could have done something different and actually gone ahead and, based on past data, given differential weights based on historical data occurring prior to 1995. But recall that one of the motivations for this, and maybe I didn't make a big enough point about this, was an awful lot of dissension. We had various people in the stakeholder group with very different ideas about whether hunting regulations should be really liberal or really restrictive. And these different groups had their different models, pet models, that they were sort of espousing, that they were interested in. And the last thing on earth anybody wanted to do was go ahead and start one model off with give them a bit of a head start and have somebody say, well, wait a minute, you're cheating. You didn't give my model equal weight to begin with. And so this was a big part of the reason for starting off with equal weights. Now, when you play with these things, you realize that sort of transient dynamics would have wiped out any such head start fairly rapidly. But for the appearance purposes, it made a lot more sense to start everything out equal. Anyway, you can see then that there's been a fair amount of evolution over time. It hasn't been necessarily very rapid, that evolution. But now a couple of the models have very, very low weights, have very little influence on decisions. One model has about 2/3 of the weight and the other model has about 1/3 of the weight. So it's not as though everything has been resolved at all, but the uncertainty has certainly been reduced in terms of what's used to make management decisions. And that's the point of this next slide here, is that this isn't just a process for learning, but it's a management process. And what does that mean? That means that we ought to be modifying our management as time goes on, that as we learn stuff. And so this is that decision matrix, and I apologize, the sort of the axes are set up a little bit differently here than they were in that toy example. But these are actual decision matrices for 2 different years, 1995 and 2013, for mid-continent mallards. And the only thing that's different for these the decision matrices themselves in terms of where the colors are fairly different. And the only thing that changed, the model stayed the same, most things stayed the same. It was just that the model weights had evolved and were very different in 2013 than they were in 1995. For example, in 1995, over half of the state space there that at least appears in this graph was liberal regulations, and that's knocked down to maybe a third, or sometimes something around a third in 2013. The little dots with the white dots with the 2 sets of confidence intervals on them end up being sort of equilibria. If the system sort of operated according to these models to the current, these different sets of model weights, over time, these would sort of be equilibria places where they would end up. Okay, so a few summary comments here. Adaptive harvest management, then, our experience with mid-continent mallards. It's reduced controversy. Arguments remain, but they have been a lot more focused than the kind of things we used to see before this process was being used. A really nice thing is that all competing models are used in the decision process, and the changes in the weights or the influence of these models isn't attributable to who had the most powerful state senator or who had the loudest voice, but to evidence-based learning. And there's something real satisfying about that, I think. The process, we can claim it's objective, transparent, scientific, and defensible. It's not perfect by a long shot. There's a whole bunch of things we can do to improve it, but it's a real honest effort to go a giant step beyond, I think, our sort of previous ad hoc process. Now, I should mention here, people shouldn't get hung up on thinking that I've made a big deal about the so-called setup phase, about establishing these 6 different components for any sort of informed management problem. And I want to make the point that at any time we can go ahead and sort of kick out of the iterative phase, if you will, and go back and revisit, say, objectives or models if we think that any of these aren't serving us well. So usually we would do this sort of stepping out of the iterative process at a time frame that would be a fair bit longer than this iterative annual process that we go through. But it's possible to go ahead and revisit some of the things that we made decisions about when we were setting up the process to begin with. And a lot of folks refer to this as double loop learning. And indeed, efforts in our mallard problem are ongoing with at least a few of these elements here. All right, and finally, just to say that this has been viewed as so much of a success by the U.S. Fish and Wildlife Service, the Office of Migratory Bird Management, that a number of other populations have now this sort of process is being used in a number of other populations throughout North America. And in fact, I think the U.S. Fish and Wildlife Service, their Office of Migratory Bird Management is widely viewed. I know I view it that way for sure. It's sort of a worldwide leader in application of serious decision theory to real world management problems. There are a couple other parts of the world where people are very interested in decision theory, but a lot of time it's much more academic. In the actual going through the tough job of actually implementing a program like this, I can't think of anybody who's done a job nearly as well as this Office of Migratory Bird Management with the U.S. Fish and Wildlife Service. Okay, 5 summary slides, and I'll be quiet here. So summary point 1 is that good decisions are becoming increasingly important in multiple disciplines, and that's something we can talk about, but I believe that really strongly, from COVID to anyway, there's some military, there are a whole bunch of places where this is a big deal. But formal decision processes, I think, are preferable in many ways. They're not perfect at all, but they're preferable in lots of ways to ad hoc approaches. But of course, the downside to this is you go through my 6 elements there and look at all the work that's involved. Clearly, formal decision processes require an awful lot more technical effort than ad hoc approaches do. There's no question about that. And so I get the point that some people could say, well, that's just too much effort. I'm not willing to undergo that. But on the other hand, I would like to think that professionalism would cause a lot of us to hopefully want to do the best we can, which in my view brings us to these more formal sort of processes. All right, summary point 3, uncertainty is often a really major impediment to decision making, certainly every decision I've been asked to comment on. And technical approaches are now available, technical approaches such as adaptive management, for making decisions in the face of uncertainty while simultaneously reducing that uncertainty. And my claim is that statisticians are pre-adapted then for supporting such processes. Statisticians are the folks who think probabilistically, and they can be, in my view, they can be really useful here. And I'd love it if more statisticians took interest in decision processes. What are the roles of statistics? Again, they are focused primarily on modeling, monitoring, and then development of these probabilistic, these stochastic decision algorithms. All 3 of these things that require technical folks, and they require probabilistic and sort of statistical thinking for sure. My last comment then is statisticians have played an essential role in the scientific enterprise. And I think I commented early on, I think this is 100% appropriate, that now I can't think of any scientific discipline where statisticians don't play a major role with the scientists of that discipline in sort of learning and, as I said, discriminating among competing hypotheses and drawing inferences. And it's my view that statisticians can be similarly important to much needed applications in formal decision processes, and especially in applying these processes to real world problems. And it's the hope then would be to not only for real world decision makers to begin to seek such help and be more interested in formal approaches, but then also for statisticians to be willing and interested in sort of joining into that process and hopefully leading to better decisions for us. Okay, I'm not sure how I've done on time, but thanks very much. And that's what I had, Mark.
Very, very nice. Yeah, thank you. We could give you a virtual round of applause. So adaptive management is sort of a very complex part of decision analysis and stuff. And I guess since I didn't see any questions in the chat, I'll ask the first one. One thing, what learning was multiple, adjusting the weights for multiple models, but not getting better estimates for each of the models or improving that. And then the other part is, I really like, if you have multiple models, I mean, we may not understand the duck example, but say we have a climate change model and we have climate deniers, they can come into the decision-making process, frame the decision, come up with a model saying climate change doesn't have anything to do with this. It's just variation through time. But then I guess the model weights or something would affect how that input, but it is a way to bring them in the room. So if my questions were understandable, do you have any comments about the way that might work?
Think so. I'm struggling here. I don't know what you guys see. I was trying to figure out how to get faces back on, and I've already forgotten what.
Oh, I think most people are actually have their videos off. It depends on the view you have. So if you want to bring yourself back to video, those that want to and aren't eating lunch, you're welcome to do so.
Okay, well, yeah, well, basically, if it's okay what you're seeing, I'll go on then. I
Yes.
don't see any video, but that's absolutely okay with me. So, all right. So the second question first for climate change, and I don't know if this is getting at what you meant, but for one of the things, when I mentioned the possibility of a sort of double loop learning and recognizing that you can change some of the models, for example. One of the things that's going on now, for example, with Migratory Bird Management Office is some of the work that Scott Boomer and I assume Emily and you guys and others have been doing, which is recognizing that up for most of the adaptive harvest management program, the dynamic model for pond numbers has basically assumed sort of stationarity, kind of Markovian stationarity. It's viewed as a first order Markov process, but it's a kind of a stationary process based on past environment. And now with environmental change, it's my understanding that there is some ability now to think of now carrying ponds once again, as you are with a state variable, but now a non-stationary state variable, which may actually change with time. And indeed, for example, if you had climate change deniers versus folks who thought climate change might be real and important, they could be viewed as two competing models in the ponds component of the adaptive harvest management process. Now your first comment so anyway, that was hopefully a response to something to do with climate change. The first comment had to do with re-estimation of parameters, and that makes a ton of sense. And that's something that once again hasn't been fully resolved yet. Was this idea of how frequently should this happen? In other words, so the idea underlying the AHM was to set out some models and allow those models to predict for a period of time without changing parameter estimates or going ahead and updating them and making them a sort of a moving target, if you will. And so, but that's another aspect that seems to me important and reasonable. And you could think of it as a flavor of double loop learning, although you don't have to. But this idea of revisiting the model set periodically and putting in your best, latest, and greatest estimates of the different model parameters that actually may be functions of the data from earlier years within the AHM program itself. And so that's something that's sensible to me and is one natural sort of improvement. And the bad thing about talking to me about this is that I apologize for this, but I retired a few years ago and I'm not as up to date on some of the things that are actually being done at the moment. And so for all I know, this is being done right now. But for the years I was involved, it wasn't, but it was something that we recognized needed to be done. This recurrent, not necessarily annually, but for every so often going back and re-estimating the parameters of the models in the model set.
All right. So I guess we could change the protocol, and why don't, if anybody has a question, look in the reactions and virtually raise your hand, and then you can come on unmute and ask. And hopefully I'm seeing everybody. So Will, go ahead. Will Siri?
Oh, I didn't have my hand up. Sorry about that.
Oh, okay.
I think Emily had her hand up.
Oh, sorry. Yes. Okay. Emily and then Phil.
Yeah. Hey, Jim. Sorry, I have a barking dog in the background. I guess two quick questions. One, in that model weight diagram, the figure you had with the model weights and that initial separation, was there something specific that led to that initial divergence of the weights? And then it seemed like there was kind of a period of time, maybe a model learning period or something. So that was one question. And then the follow-up would be, talking about that decision process and incorporating statistical expertise. In your experience, I mean, I certainly agree with you, in decision processes that I've been a part of, we always hit a point where you have to think about how to incorporate some of the uncertainty, or how to formalize some of the thinking about how your understanding of the system would work into some kind of predictive model. Sorry. Anyway, just more thoughts on how specifically the statistical expertise might get incorporated into the decision process.
Okay. The first one, I can't answer in a mechanistic sense. I can answer it in a phenomenological way. Basically, that 1 year when you had some fairly substantial changes early on was a year when population size, the actual estimate, it far exceeded predictions of any one of the models. And so it ended up that the model that had the highest prediction basically ended up getting more weight, but it was an anomalous year in that sense, in the sense that none of the models did well. Just as an aside, if that happened all of the time, in other words, if all the models always way under predicted or way over predicted, that's a real big red flag that says, hey, this is a time for this double loop learning step where I better darn well go back and look at my model set and try to figure out what's missing from them, or what's going wrong, to try to make it so they did a bit better job of predicting. But basically, that 1 year was anomalous with respect to all the model predictions, and the understanding, or at least I don't have the understanding to know exactly why. So with the idea of, so the second question had to do with statisticians basically, or let me paraphrase and see if I get this right. Would they be useful in trying to develop models of how things worked by perhaps meeting with the non-statistical folks who had good understandings of those particular systems? And if that is anywhere near being okay, that's exactly what can happen, and is a real important role of statisticians is often in these workshops. There's a nice set of workshops that the Department of Interior has developed at this, as you well know, Emily, at this National Conservation Training Center, trying to teach sort of various aspects of decision making to anybody who's interested. And one flavor or one class of their offerings are basically workshops where you bring together a group of people who are interested in a particular problem, subject matter experts in a particular management problem. And usually you have one or two statistical or sort of technical folks at a minimum with them. And the idea then is to do exactly as you say, to try to lead folks through a rapid prototype of an adaptive management process. It usually takes about they're given 5 days to do this. And a big part of that is trying to extract the essential features from knowledgeable people that will allow you to build these predictive models. And of course, this is just a silly aside, if you ever try to do these things, one of the most difficult things is that everybody always knows lots and lots and lots of detail. And models, by definition, are abstractions. And your job as a modeler or a technical person is to try to view the modeling process as a filter and sort of keep or retain the stuff that's absolutely essential to your predictions and get rid of all the other stuff. And that's an interesting process going through that with a group of knowledgeable people. Anyway.
All right. Thank you. Phil, you're up.
Hi. So really quickly, because it's late now. First, Dr. Nichols, thank you for your presentation. I think I disagree with you. You said you don't consider yourself to be a statistician. I'm sure you are. And one of your slides, you talked about other disciplines other than natural resource management, where perhaps people should be applying approaches such as you've described. Can you talk for a little bit about what disciplines you think should be doing this?
Well, I can talk about a couple, but in a way, the one thing I ask you to do is be cognizant of me just talking off the cuff here, because yeah, but I'll go ahead and do that. So I ended up finding myself in a workshop with some folks from the Centers for Disease Control, two different workshops basically, and I was struck by and again, it was no claim that their best biologists or statistical folks were there. I don't claim that at all. But what was bothersome to me when I heard about approaches, number one was approaches to estimating things. And I think this notion of, the kind of false positives, false negatives, anyway, ways of dealing with things. I think we had lots better ways of doing it than is being done with respect to estimation. But then with decision processes, that was very much was very upsetting to me in the sense that things are done basically the way we used to do in the old duck days. And so you have these people devoting all kinds of time and effort to estimating things like infection rates and things of this nature and prevalence, and then in ultimately a group of experts, and there's not a pejorative term at all, real experts, get around and basically say, they look at that stuff and they say, well, I think this is what we'll do for our vaccine this year. And it's okay. And there's no claim that they're necessarily making bad predictions, but it's just bothersome to me. And I make a silly statement here, being a wise guy, but I say, imagine you sitting on a witness stand and a judge or somebody is, a lawyer for some opposing group is asking you about a decision you made, and his suit costs more than you make in a month probably. And you imagine how comforting it would be if you could say, well, I made this decision, and given the objectives that we all agreed upon, given the actions that were available to me, given my understanding of the system as encoded in the models that we use and our estimates of system state, I made the smartest decision I could have made, and I can prove it to you. And I always think of that as being a nice thing to be able to say, and yet it's embarrassing to me that in a lot of places now in society, I don't think we can say that. CDC was one example. I got my son-in-law is a military strategist. We've talked about this with him as well. There are just a whole bunch of places, I think, where this could be useful.
Thank you. I think we're a little beyond time, but I guess I just wanted to say too that, the modeling and the adaptive management, there are also approaches called structured decision making for one-time decisions, and not all parts of this need to be used for all problems. And Jim gave a little idea of different examples, and I can put up a number of resources that we could use. But given that it's over time, Jim, thank you very much for a very informative talk in an area we don't often hear about. So thank you very much.